My name is Nick Ballering. Today I'm going to talk to you about observing disks and proplyds in the Orion Nebula cluster with ALMA at 3 millimeters. So the ONC is one of the nearest regions of clustered star formation, and it's a great laboratory to understand the effect of dense clusters and more extreme ultraviolet radiation environments on disks and planet formation. So the story starts a few years ago when Josh Eisner led a program to mosaic the inner 1.5 by 1.5 arc-minute region of the ONC with ALMA at band 7. And that program detected over 100 disk sources. And so you can see in the distribution to the right, a histogram of the disk sizes. And what we found is that the disk sizes in the ONC, seen here in red, are significantly smaller than disk sizes measured in lower mass star forming region. And that's interpreted as direct evidence that these disks have been truncated by the external photoevaporation from the strong UV field in the ONC. So we got some follow-up observations at ALMA band 3, and that's what I'm going to talk about today. And so we achieved a resolution of about 60 milliarcseconds, which corresponds to 24 AU at the distance of the ONC, a sensitivity of around 30 microjanskis per beam, although that varies across the mosaic. And the goal was to measure the disk masses, their sizes, as well as the spectral indices between band 7 and band 3. And so the dust masses that we can measure are given by this formula, and there's a healthy dose of skepticism you should take from any dust masses measured this formula, because you have to have assumptions for the dust temperature, as well as the opacity, and the assumption that the emission is entirely optically thin. So I'll also note that these new ALMA observations are not yet published, so you can think of these conclusions as still a bit preliminary. So one of the things that we see in our observations are proplyds. And if you're not familiar with what a proplyd is, it's a disk that is actively undergoing external photoevaporation. And they show this sort of characteristic teardrop or tadpole-shaped structure where the disk is being evaporated, and you can see this ionized cocoon of material surrounding the disk. And so usually when you study proplyds in the sub-millimeter or millimeter or centimeter regime, you can measure the dust, but there's also emission from the free from that ionized plasma. And so if you have spatially unresolved observations of proplyds, you need to decompose the spectral energy distribution into a dust component as well as a free component. And so that's what's shown here, that you have to measure the free out at centimeter wavelengths and extrapolate back to subtract off the signal from the dust. So I'm going to show you is a subset of proplyds from our new data. And these are shown here in these 4 systems. So in the top panel, you can see what you might see is the picture of the proplyds you recognize from HST, where you have the head of the proplyd and these long tails of ionized emission. And in the bottom panels, you can see what they look like at ALMA band 3 at 3.1 millimeters. And you'll notice we see 2 distinct peaks of emission, and that's because we're picking up both the free emission from the ionized gas in the proplyd, as well as the dust emission from the disk. And what's nice is that at these high resolutions, we can spatially separate the 2. And so what we found is that there really is not much free emission coming from the disk itself, and there doesn't seem to be much dust emission coming from the proplyd head, at least large dust emission. And that point is driven home by these contours. So the red contours overlaid are VLA images at 1.3 centimeters from some of Patrick Sheehan's work, and the black contours are the band 7 data from Eisner 2018. So if we just now focus on the disk components and try to measure their properties, we can see that their sizes are 13, 17, or 34 AU, which is on the smaller size of disks, but fairly comparable to what was derived from the band 7 data. And the dust masses are tens or a little over 100 Earth masses, which is not terribly small. The spectral indices between band 7 and band 3 come out to be about 1.6 or up to 2.0, which is again on the shallower side for spectral indices. So I'm going to tell you a little bit about our interpretation of the low spectral indices. So first I'll note that our spectral indices are sort of on the lower end of what else has been measured for disks in other regions, but not completely off the chart. So here's a nice work from Tezzari et al. From 2020, measuring the spectral indices out to 3 millimeters. And they do see, a tail of their distribution down around 2 or a little less. So how to interpret spectral indices? The classic picture is that the dust opacity spectrum has a spectral index beta. And so if the emission from the disk is optically thin, and you further assume that it is in the Rayleigh-Jeans regime, the spectral index you measure should be 2 plus beta. So we can measure the spectral index, subtract 2, calculate beta, and infer something about the grain sizes. So a low alpha corresponds to a low beta, which would indicate that the grain sizes are large. However, there are some complications to this picture due to the potential for high optical depth, and I show that in these panels below. This is the results from a suite of radiative transfer simulations that I ran last year with Josh Eisner. In each panel, the x-axis is the disk size and the y-axis is the spectral index out to 3 millimeters. And each panel corresponds to a different model dust mass. And so the beta for this model is about 1. So what you'd expect to measure, given this simplified picture, is about 3. However, what the models actually return for the spectral index is shown in this black line. And you can see it can deviate quite a bit from that naive expectation. And especially can deviate for large disks and small disk sizes, which might be more of the regime we're in. And this again is due to the high optical depth in that case. And so that can push the measured spectral indices down closer to 2. There's also a further complication from dust scattering, and that can be have an effect if the grains are both large and the disk has a high optical depth, and then you have to worry about complications from the grain albedo as well. So the general conclusions that we've reached so far from this data set is that we've obtained a nice high-resolution deep mosaic of the ONC, and taking a closer look at some of these proplyds, we can reveals that the dust emission can be isolated from the proplyd free emission. So we can disentangle them spatially rather than just spectrally. We find that the disk sizes are small, which is in rough agreement with the band 7 results, and that the spectral indices are also small. So I'll say stay tuned as we work our way through the rest of the sources in our data set and put these results into a larger statistical context.